before. So he's doing the devising. His name is Michael. Moon. Engineering 3. Email address and the office hours. The second here will be doing the homework grading, and he also could come here and teach the lecture for me when I type. So his name is Sai. Office in 434 Harris Engineering Center, and also the email address. Yep. Now I don't think you need his office hours because he's basically just doing the homework grading. But if you have any question about the grading, you can send him an email and make an appointment with Sai. Right? For the advising, you can always go to the office at any time, and the person can help you with some homework. All right. So last time we started to talk about the series and the parallel combinations of resistors. I'd like to go a little backward today because I may have gone too fast. Considering your background, you have no background. So I tend to go too fast sometimes because sometimes I forgot that I don't have any background here. Okay. So when I put a resistor like this, the symbol. Right? So that represents a piece of material that has certain value of resistance. Okay. Now, if you'd like to see the photos of resistors, it's on page 15. So this is all. So page 15 in the book. Okay, so there are many different types of resistors. Some are smaller at the bottom, right? Some are larger on the top. Now, you may be wondering why we have different sizes for the different resistors. Is the smaller one has a smaller resistance, and the larger one has a larger resistance?
Not necessarily.
Is it so?
Not necessarily.
No, it's not. The size of the resistors has nothing to do with the resistance. The resistance is decided by the makeup of the material. Okay, now you can see in the middle, right? It's a piece of material. It's coated, of course. Huh? Okay. And that material will provide certain level of resistance. Now, what type of material do we use? Sometimes we use copper. Sometimes we use some composite materials. And the density of the material can decide the resistance. Yeah? Okay. And the reason for the metals on both sides is to conduct the current, right? Again, as I mentioned, you have to use a conductor to conduct the flow of charge, which is called current. Yeah. Okay. Now, the smaller resistor, the size, can handle smaller power, and the larger resistor can handle larger power. Okay, the power is equal to the current times the voltage. Okay, so when I have a voltage across the resistor, I get a current, right? According to the Ohm's law we discussed last time. Okay, so the larger the current, the larger the voltage, the larger the power. power can be destructive. Yeah? If you have high power on a resistor, you can burn out the component. So, depending on what type of power you can have, you would have to select the different type of resistors, right? Because if you have a large power, then you have to use the larger size. If you have a smaller power, you use the smaller size. Yeah? According to the Ohm's law, the current is equal to voltage across the resistor divided by the resistance. And this is in amp, this is in volts, this is in ohm. Right? These are the units. So what happens if I take away the resistor? Huh? If I just have a piece of wire?
Sure.
Theoretically speaking, that piece of wire has 0 resistance. But in reality, that's not true. Any metal has a finite resistance, even though it's very small. Okay? There's no such thing as 0 resistance. Got it? Okay. But if you have a piece of metal, then normally we say, okay, the resistance is almost 0. All right. So that means if you have a voltage across just a piece of wire, the current will be very large, right? Because this is almost 0, right? And that will be the case if you, let's say you stick a wire between the 2 outlets on the wall, yeah? Then you're going to get a huge current between the 2, you have an outlet, right? Outlet, and there are 2 socket, right? Okay, so if you stick a wire across it, you're going to get a huge current. And so when you do that, you don't want to try this at home. But when you do that, what's going to happen is that there is a circuit panel in your house or in your apartment. Okay? And the circuit panel has switches. And the purpose of the switches is to open the circuit when it detects a very huge current in the network of the house for the protection purposes. Okay, so when you do this, a switch in the circuit panel would trip, would open. Got it? Okay. But in the early days, there are no switches. Okay, so what do? We use a fuse. Got it? A fuse. A fuse is something that will melt when a large current flows through it. Yeah? So again, purpose of a fuse is to open the circuit when a large current is detected. Again, for the purpose of protecting the electronic system. Okay. And also, when we draw the network, okay, sometimes we do different things, okay, but different things can mean the same thing. Okay, for example, if I draw something like this, R1, R2, right? This is the same as, okay, it's the same thing, R1, R2, right? And sometimes if I do something like this, R1, R2, then it's the same as because even they look different, the node, connecting nodes are the same. Yeah? The same is here. The connecting node is right here, right? For this series combination, and that node is where? Right here, right? It's the same node. So as long as you have the same connecting node, doesn't matter what is the geometry of the network, they are the same. Okay? Okay, let me do a few more examples about the parallel and the series combinations. Okay? Before we move on to something that's important also. Okay? Okay, let me do, I took this one from the book. Okay, so we want to find the equivalent resistance between terminal A and B. So that's called R and B. Now K means what?
1,000.
Yeah, K means 1,000. And most of the time, just I skip the unit. Okay, I supposed to put a unit right behind every one of this, but sometimes I just get lazy. Yeah. Okay. When you try to find the equivalent resistance for these two terminals, and because the terminals is located on the left-hand side, so normally you want to solve this problem from the right-hand side, from the opposite side of the terminals. Okay? Now you have to realize what are in series and what are in parallel. Are these two in series?
No.
No, because of that. Got it? I told you yesterday, last time that would be in series, but if there's another connection right here, then you would not allow to use the series formula for these two resistors. Right? Okay. So the first thing to do is to do this combination. Yes? Now, so these two are in series, correct? Because there's nothing connected to the middle. Okay. So these two will give you what? 9K, correct? So we have 18K, 9K, and this is 6K. Yes? Yeah.
When you added that 3 and the 6, why did it go on to the other side and not stay on top?
Oh, if you like, I can put it on top.
I was just curious if it was the same or if it...
It's the same.
Okay.
It's the same. As I just tried to explain to you from this side, right? It's the, you put it here, or you put it here, it's the same. Yeah. So this is 9K. So now you can see that the 9K and 18K are in parallel. Yeah? Okay? So therefore, 9K and 18K in parallel, if we use the formula I gave you last time, this will become 6K. So here, goes down here, 6K, 6K, and then you have 10K. Yes? All right. So now we have all three in series. Yeah? So therefore, the final equivalent resistance is what? It's just the sum of the three. Huh? So 12K and 10K, 22K. 22K ohm. Yeah? So that's the answer. Okay, let me do one more. Again, we'll find the equivalent resistance from the terminals A and the B. So you go to the opposite side, right? And then you try to solve the problem from the right hand side all the way to the left. Okay, so now first you see that these two are in series, yes?
Yes.
And they give you 12K in series, and then you have a 12K here. And then you have something here, right? And then the rest. So the 12K and 12K are in parallel. And you use the formula, you're going to find that the two parallel become 6K, right? Okay, so you get 6K, right? And then you have this 3K, you have 4K, right? And then you have a 6K here. Now you see the way I drew like this is the same as that. Got it? It's all just a piece of wire. The same connected node. Right? Right now what? Are these two in parallel? Right? Because they have two common connecting nodes. Yeah? Of course, that's the same as that. Huh? It's the same, huh? Okay, so 3K, 6K will give you 2K. Right? So this is 2K. So keep on going. Actually get 6K, 4K, 2K. Yes? Because these two have become a single resistor of 2K. Now these two are in series again. Yes, so you have 6K, 6K, yes? So finally, yeah, so finally this two in parallel, so your final answer is 3K. Is it not too difficult? No? Any question? Yeah.
So on the first example we did, the 18K and 9K are parallel, right?
Yeah,
And then the 18K and 6K are not parallel, right?
18K and 6K right here,
Yeah, they're not parallel. Right?
they are not in parallel? No. Why?
They don't
Because there's only one connecting node. Where's the second connecting node? In order to be parallel, you must have two common connecting nodes. This, right? It's not.
The 18K and 9K is the node in the bottom right.
Yeah. 18 and 9K, you have one connecting node, you have the second. The second connecting node. Okay. I'll give you the first homework assignment today, but it's not due until maybe, I don't know, 2 weeks or so, just to get you started, okay? So get started to do some of the homework problems associated with chapter 2. Now, I'm going to introduce two very important laws. The first one is called Kirchhoff voltage law. Okay, this is called KVL. Okay, and then the second one, the same name. Current law, KCL. We'll be using this laws many times in the coming lectures. Okay, so let's talk about KVL first. KVL. It states that the algebraic sum of voltage drops and rises in a closed loop is 0. Okay, the best way to explain this is to do a couple of examples. so we have a circuit that consists of a voltage source with some voltage and two resistors in series. Huh? Okay, first of all, when you have a voltage source with the polarity like this, the current that is generated by the voltage source is always go from the minus to the plus. Okay, current. The direction of the current always go from minus to the plus, okay, from a voltage source. Okay. Then when the current going through the resistor, you would have the voltage drop, plus and minus. Let's call this V1, right? Because the current is going this way, the current going this way, so you're going to get a voltage drop. It's called V2. Yeah.
Now, when the voltage source is flowing towards the positive, does that mean that the resistors that's flowing towards the negative then?
I did not get your question.
Well, with the voltage source, you have the flow from negative to positive, but you wrote it as positive and negative on the resistor.
Oh. Okay, this is based on the Ohm's law. Okay, the Ohm's law will tell you the following, right? If you have an R here, right? And if you have a current going this way, then the voltage on the resistor must be plus and minus. Okay, that's the Ohm's law. Very simple. Now, why is that? Because, as I said, the positive means you have more electrical potential here, and this is the lower potential. And the current will tend to go from the positive potential to the low potential. Right? But that concept does not apply to the, well, actually it also applies to the voltage source. Why? Because the current, the flow of the charge will go from the positive to the negative, right? So it's the same concept. So the current, that's why the current goes this way, because we will start from here, right, and then go to the negative. Okay, the polarities of all these components are very important. Okay, because if you look at the direction of the current, which is the clockwise direction, and then you can start from a point, and then you go around the loop. You need to go back to the same point, and that becomes a closed loop. Okay, I want to emphasize closed. So basically, you can start from any point as the starting point, and then you go around the loop. You have to go back to the same point. Okay, so where do you can start from here? Okay, that will be my starting point. Then you follow the direction of the current. You can see now you have a voltage what? If you go this direction, it has a voltage drop, right? Because you go from the positive to the negative. So you have a voltage drop. On R1, that's called V1. Yes? Okay, then you go to here. You see a second voltage drop on R2, and that's called V2. And then you go around. Now you see a voltage rise, right? Because it goes from minus to plus. So you get a voltage rise, which is V. Right? V. Okay, now we're going to apply the Kirchhoff voltage law. Right? It tells you that the sum of voltage drops and rise in a closed loop should be equal to 0. Right? So if I just add them up, but we have to assign the sign to the drop and the rise. So normally we would use the negative sign for the drop, and we use the positive sign for the rise. therefore, I have minus V1 minus V2 plus V equal to 0. According to the current of voltage law. Right? All right, so let's do next example. I can this time can assign some numbers. So now we see we have a circuit that has 3 voltage sources and 3 resistors. Huh? So I want to find out, I don't want to find out the current, so I want to find the current in the loop. Yeah? And also we can say I want to find out what's the voltage drop on the 3 ohm resistor. Okay, now, do you think I know the direction of the current at this time?
No.
It's not possible to know the direction of the current. For this circuit, it's easy, right? Because you only have 1 voltage source, so current must be going this way. But here you have 3 different voltage sources, so it's not possible. Okay, so what you do is you just go ahead and assume the current direction in the beginning, okay? And then at the end, if you get a negative value for the current, that means the direction should be the opposite. Got it? Okay. So I'm going to assume the direction. This. Huh? All right. So if the current going through this direction, then the voltage on 2 ohm will be what? Will be plus or minus. Let's call this V1, right? The voltage here will be what? Plus minus V2 plus minus V3. Again, the polarity are important. They have to be consistent with the direction of the current. Yes? Okay. So, now you can pick any points you like as the starting point. And then you go around the loop and you go back to the same point. Okay? So where do you want to go? Let's start from here. Alright? Okay. So now, once you have picked the starting point, you follow the current direction. What do you have? That's a voltage
Negative.
drop. Minus 2 volts, right? Is plus 4 volts because that's a rise, yes?
Mm-hmm.
And minus 5 volts because that's a drop. And all these are what?
Minus.
Are drops. So minus V1, minus V2, minus V3. And then now we return to the same point, right? So it's equal to 0.
It's not possible.
Huh?
It's not possible.
We don't know. We have to find out. Okay. So what's V1? According to the Ohm's law, V1 is what? I times 2, right?
Yep.
Okay. So what do you have on the top? It's minus what? minus 3, right? So minus 3 volts minus I times 2 minus I times 1 minus I times 3 equal to 0. Correct? Because the voltage on the resistor is the current times the resistance, according to the Ohm's law. So I get what? How many I do I get?
3.
6. Huh? 6I, right? So minus 3 volt minus 6I equal to 0. So therefore, what is the current? Current is minus what? 0.5 amp, correct? So that minus sign indicates that the current should be in the opposite direction. So the current actually should be, so that's not the direction. It's the current. Okay. Next question. What is the voltage on the 3 ohm resistor? That should be easy, right? Once you know the current. So the voltage on the 3 ohm is what? We call V3, huh? So voltage on the 3 ohm is the current times 3 ohm, and the current is 0.5 amp times 3 ohm, so that gives you 1.5 volts. Yes? And what's the polarity of that voltage, by the way? Huh? Because the current is going in this direction, correct? Yeah? So therefore the voltage should be where? Should be plus and the minus, and the magnitude of that voltage is 1.5.
When we do the equation and we get the amperage in negative, usually the other way is just the same number in positive?
Yeah, you just look at the plus or minus just indicates the direction.
Oh, okay.
Okay? And that is the magnitude of the current.
That's supposed to be negative 1.5 volts?
Huh?
Negative 1.5 volts?
Yeah. Minus 0.5 volts.
That's
I'm sorry, minus 0.5 amp. That's the current. And this is the voltage on the 3 ohm resistor is 1.5 amp. Okay, now, based on the KVL, we can derive a rule. That's called the voltage divider rule. Okay, and this rule can be quite useful sometimes. So basically, we tell you that if we have several resistors in series, let's say this is R1, this is R2, this is R2. Okay? And this is terminal A, this is terminal B. And let's say the voltage between the two terminals of B, A, B. Now, when I write B, A, B, of course, A and B are in substrate, right? This means terminal A would have a higher potential than terminal B. Okay? Now, if I write BTA, then that means terminal B will have a higher potential than terminal A. Got it? Okay, that's the conventional notation. Okay? So that means, if I write this way, then this must be plus the voltage, then this must be negative, right? And obviously there will be a current going from the plus to the minus, right? Okay, and so this is the current I, and I'm going to call this V1, this is the voltage drop V2, this is the voltage drop V3. Yes? Okay, then, according to this rule, V1 can be expressed in terms of VAB in the following formula. And V3, the same thing. Okay? Now this formula is not limited to just 3 resistors. It applies to any number of resistors in series. Okay, any number. Okay? So let me do an example quickly. Let's say I have a voltage source, 10 volts, right? And then I have, let's see, I have 4, right? Okay. 1 ohm, 2 ohm, 3 ohm, 4 ohm. Yes? And let's say you want to find the voltage on the 4 ohm resistor. Okay? You want to find the voltage of the 4 ohm resistor. Yeah, 2 ways to do this. The first way is to use the Kirchhoff voltage law, we just did. Right? We try to find out the current in the loop, right? You can sum up all the voltage rise and the voltage drops to be 0, and then you can calculate the current. Once you know the current, then you can use the Ohm's law, you can get the voltage. Correct? You do that. But if you use the voltage divider rule, it will be faster and easy. Okay? So now you can see the voltage on these 2 terminals is what? Is 10 volts, correct? Okay. So therefore, between the 10 volt you have these 4 resistors in series. So if I use the formula here, I can just one equation, I can get the answer. So the voltage on the 4 ohm, is equal to what? If we just look at the formula. It is the total voltage, right, which is 10 volts. 10 volt times the sum of all the voltages, all the resistors in series. 1 ohm plus 2 ohm plus 3 ohm plus 4 ohm. Yes? In the denominator. And then what is on the numerator? Yeah, that's right. So with this single equation, you can calculate the voltage drop on the 4 ohm. Yeah? Now, if you want to, of course, you can apply this to the voltage drop on other resistors. So let's say you want to find the voltage on the 2 ohm. Then it's the same thing, right? 10 volt times this kind of what? 2 ohm on top, right? 1 plus 2 plus 3. Can I use what? Oh, yeah. Once you know the voltage, you can divide the voltage by the resistance and give you the current. Right. Okay, I think we better stop here because I don't have enough time to do it. All right. Oh,